So I might just. Wrestling driving down. Yeah, I'm not. Not only are you it's not going to the same place. Ramsey or Sirius? Ramsey. Sirius is going to the same place. I could ask him. I really. It's also driving.
No, go for it.
Okay, guys, page 13.
Oh my God. She's like, man, why did you feel like 19? Let me tell you.
Okay, so
the topics I want to highlight today are first derivative test, test for concavity, and then second derivative test. So okay, let me just read through these some of this review here. So first derivative test, this is where we use the f prime and the sign line to determine the location of a relative max relative min, as well as the increase and decrease. Okay. So first we find f prime, then we set f prime equal to 0. If there's a numerator and denominator, we have to consider both the numerator and denominator. Then we place all the critical values onto our sign line, and then we test each subinterval. So now this should feel familiar since we've been using this recently as well. So let's look at number 1 here. It says, at what value of x does our function have a relative minimum? So we're trying to do this without a graph. So let's find f prime. Set f prime equal to 0, both numerator and denominator, and then we'll test each interval with our sign line. Okay, so f prime first. The nice thing is that both these terms are set up and ready for power rule, so we can jump directly into power rule. X becomes 1, and then we bring the 2/3 down.
just forgetting.
She's not gonna
Sure.
finish.
Okay, and then we subtract 1 from the exponent, so 2/3 minus 3/3 is equal to what? Negative 1/3. Okay, so let's clean this up here. So f prime equals. Okay, I'll put this back down in the denominator. Now, this is actually a little bit more involved than what we would expect, because we actually have to merge it into a fraction so that we can have an easier time finding the critical points. It's easier to find critical points if we have, that way we know exactly where to look. So I'm gonna have to find common denominator. What's my common denominator here? Yeah, 3x to the 1/3. So I need to balance each of the fractions. Now this one's easy to balance because the numerators will also be 3x to the 1/3. So now it's a little bit cleaner here. Now I have my numerator and denominator merged together into one fraction. And now I can set both the top and bottom equal to 0. And those are my critical points that I can place onto my sign line. Okay. All right, so numerator first. What can I do to both sides to get x by itself? Raise, not cube root, but to the third, right? Because I know that 3 and 1/3 will cancel out. So x equals 4 cubed over 9 cubed, so 64 over 27. And also the denominator. And the reason why we also look at the denominator is because we want to look for places where slope is undefined, because that could be a max or min, right? Slope undefined could be a sharp turn that could end up being a peak or valley. Okay, so here, this is pretty easy though. Divide by 3, cube both sides, still ends up being 0. So we have two critical points, 64 over 27 and 0. Okay, so we have 3 intervals to test. I'll test -1. I'll test 1. And then 64/27 is less than 3, so I can test 3 as well. Now, I'm testing these points up against what? Well, the original is going to give us location, but derivative, because right now we still want to know what the behavior of the graph is. We still don't know whether it's rising or falling. But once we know what the behavior of the slope is, then we can decide where the relative min is. So we're going to insert into this derivative function. Thank you. Okay, so insert -1 here. So cube root of -1 is still -1. So -1, 3 minus 4 is negative over a negative. So 2 negatives makes positive. We know this interval, my graph is increasing. All right, insert 1 in. I get 3 minus 4, that's negative. 3 is positive, so negative or positive is negative. Insert 3 in. 3 times the cube root of 3, a little bit more than 4, so it's going to be positive over a positive. Okay, so now we can look at the arrows and decide where that relative min is, right? So where's our relative minimum? Okay, right. So, but here it says, right, it says at what value? So that will be 64/27. But what if it was asking for what is the value of the relative minimum? Then we're asking for the y value. So if that's the case, you would insert 64/27 into the original function. But here it says at what value? So yeah, 64/27. Double check real quick. Yeah, okay. Okay, number 2, this is a concavity test, or we also say this is test for concavity. So this is where we do the same steps as what we did up here, but it's for the second derivative. Right, so we can find f double, make our way down to f double prime, create our set f double prime go to 0, find our critical points, test our sign line. But now, if we're dealing with the second derivative sign line, now the change in signs will indicate not a relative max, relative min, but a point of inflection. So, okay, so we're going to make our way down to the second derivative function. And then both we can just handle using power rule. Okay, set equal to 0. GCF, what's our GCF? 12x. Right, critical points. Yeah. And 0. So y double prime, sign line. This is, I just want to point out, this is a common mistake that students make, is that when asking for point of inflection, some students would just get to the critical points and they would just stop there and they would assume that every critical point is a point of inflection. But we have to go through the sign line because we have to double check that there's actually a change in signs. Okay, if there's no change in signs, it's going to just be a critical point, but it's not a point of inflection. So just be aware of that. That's something that's very common because it just feels like we're done once we solve for x, but we still have to go through that sign line test. Okay, so y double prime, we're going to insert, test some values here. We can take these values in between and insert into the what? Second derivative, yeah. So because we want to gather the information about concavity so that we can decide whether to identify that interval as concave up or concave down, okay? And you can plug into either variation of second derivative, but it just feels easier to plug into the factored form because you can just gather your signs a little bit quicker rather than having to calculate larger values. Okay, so negative in for x, 12 times -1, that's negative. Negative 1 minus 1 is negative. 2 negatives makes positive, so we know that this interval is concave up. 1/2 in for x, that's positive, times 1/2 minus 1 is negative. Positive and negative makes negative. Okay, plug 2 in. So positive times positive. So in this case, looks like both my critical points ends up being point of inflection, but we really need to still go through and test and check because we can't always assume that there's always going to be a change in signs. Okay. So we can insert these back into the original function, but it's kind of easy to tell that answer choice B. Okay. Any questions there with 2? Okay. This is one that I want to point out because second derivative test is not the same thing as test for concavity, even though it feels like that would be the name for test for concavity. The second derivative test is kind of like a roundabout way of doing the same thing as the first derivative test. Okay, it just feels more complicated. Typically, if we want to find relative max, relative min, I think most students will just prefer to go through the first derivative test. But the reason that we have to know about the second derivative test is because sometimes a problem forces you, or the problem forces you into knowledge of second derivative test. Okay, so here's the idea, is that we use the second derivative test to find the same thing as the first derivative test, which is the relative max and relative min. Right, just another way of finding max and min, but it's using the second derivative to help us get there. So what we do is we find f prime, we set f prime equal to 0, and we find a critical point. So those are the same things. We're going to find the same candidates the same way that we do first derivative test. But then after that, things are different. We're not going to create a sign line, but instead we're going to take these critical points and we're going to insert into the second derivative function. And then we're going to look to see what number we get. Okay, if we get a negative number, we know the graph is concave down. If the graph is concave down, we know that paired with a slope 0, that point must be a what? A relative max. Yeah. And if I insert a value into the second derivative and I get a positive number, that means it's concave up. And if the graph is concave up and it's paired with a slope 0, we know that must be a relative what? Relative min. But it's easy to get this mixed up because if you see the second derivative, let's say value being 15, it just feels like a large number should be a relative max, right? Because it just feels more natural. Or if I say like f double prime of 1 is equal to -16, I think the natural tendency is you want to say that is a low value, so therefore that's a relative min. Now, these are not order pairs. These are not locations. These are not even slopes. These are concavity values. So we have to just recognize that this is meaning it's a curvature that has concave down. So it's actually pointing to a relative max. So just have to know that this feels a little bit abstract because it's not something that we can pinpoint. It's not a slope. It's not a order pair. This is a concavity value. It's a curvature value. Okay. So okay, so it's just an example here. All right, let's look at number 3 here. It says if f prime is equal to 0. So let's state out what this means so we can kind of verbalize or visualize what's going on. What does that mean when f prime is equal to 0? That means at x equals 5, what's happening? The slope of my graph is 0. Right? There's different variations of it. It could be looking like this. It could be looking like this. It could be looking like this, right? It could be any of these variations of slope zeros, right? But we just know that there's a slope 0. We don't know what type, but at least we know what's happening there. F double prime of 5 is equal to -3. Can you interpret this? What does that mean? That means the graph is what? Concave what? Down is less than 0. Okay, so concave down at x equals 5. Okay. So if we know that there's a slope 0 and the graph is concave down, what can we conclude? There must be a what? Relative max, yeah. So we can say by the second derivative test, which you actually don't even have to say that, you just have to indicate the reasoning. So since the slope is 0 and the second derivative is less than 0, there must be a relative max at x equals 5. Okay, even though we don't know where that order pair is, but just from the slope and concavity information, we can make this conclusion. So I remember on the test, in first semester, a lot of students would not know how to interpret that. They would feel like that's an ordered pair and they would try to plot that point, but this is kind of like an abstract value. You just have to know that it tells you the curvature and that curvature is opening down. Okay, we've seen derivative graphs as recently as this previous quiz, so hopefully it feels more familiar because we've been working through it. So let's just look at number 4. I think we understand a lot of this here. So given our f prime graph below, find the identify the following characteristics. So given the f prime, we have to know that this is not the shape of the original graph, but we can create a slope and concavity sign line to help us get a more straightforward look as to what the graph looks like the actual function looks like. Okay, so we know if we're dealing with f prime graph, we like to go ahead and label what we're working with. Anything above the x-axis is positive slope. Anything below the x-axis is negative slope. Anything on the x-axis is slope 0. Okay, so from that, see if you can create your slope sign line. And then your concavity sign line, or second derivative sign line. We want to pick out points of inflections, right? And how do we find out points of inflections off of this first derivative graph? Peaks and valleys, right? So we look at the peaks and valleys, find the x values there, and then the negative slope corresponds with concave down, positive slope with concave up. Okay, don't look at the shape here. So this is not concave down and concave up. This is not the original graph, so we can't hold the concavity information like we normally would. Okay, so spend a minute, see if you're able to fill out these sign lines. And once you have the sign lines filled out, then this is easy because you're just reading the sign lines to fill out everything. Right, but you're going to start at -4 and end at 7, both. These are now going to be the critical points. And one more though. And
Okay, so critical points of slope zeros are the x-intercepts, so -2, 1, and 5. Above the x-axis, don't look at the movement of the graph, look at the location. Location is clearly above, so that's positive slope. Below is negative slope. Above represents positive slope, and then still positive slope. So this is really the true shape of the graph, even though we don't know the physical locations. We know the graph is going to move in this way. So it's going to have a relative max at -2, relative min at 1, and it's going to rise, flatten out, and continue rising. So neither a relative max nor relative min. Points of inflection, the peaks and valleys. So points of basically the steepest points on the curve will be at -1, 3, and 5. And then now you look at the slope. Okay. Negative slope is concave down, positive slope, concave up, concave down, concave up. And once you have this in front of you, then filling this out becomes a lot easier. Right. So on the AP exam, if you see asked to justify your answers, then you're going to write these because statements. Okay. A couple of things I want to point out is if you say because, you can't. If you say because the graph changes or because it changes, that's not good enough, right? So you want to be able to really specify and name what you are describing. Okay, so just want to point out those things. Yeah, because graph changes signs, right? So that's not good enough, right? So make sure you specify what you're referring to and be very specific. For relative max, relative min, you have to specify the order of your sign change, but for points of inflection, you don't have to. You can just say that left or prime changes signs, and that's good enough. There's no distinction in name between positive to negative, concave up to concave down versus concave down to concave up. Okay, any questions? Okay, let's look at particle motion. Okay, so particle motion is position, velocity, acceleration, and that is the relationship in terms of the derivatives. Function is kind of like your position is kind of like your original function. Velocity is kind of like your derivative, first derivative, and then acceleration is your second derivative. Okay, so particle motion, we're going to find velocity, set velocity equal to 0, create sign line. So we're basically creating a sign line very much like how we do with first derivative test. It's just that now instead of calling it f prime, we're calling it velocity. And then a couple of things to note is if we're trying to determine whether speed is increasing or decreasing, we compare the signs, right? If the velocity and acceleration have the same signs, particle speed is increasing. If velocity and acceleration have opposite signs, particle speed is decreasing. So number 5, position is given. For what value is the speed of the particle increasing? So this is asking us to compare between velocity and acceleration. But it's not just asking for whether the speed is increasing at a particular value, it's asking for a range of values. So what we're going to do is we're going to find the velocity graph, find the acceleration graph, sign line, sorry, and then we're going to test each interval, and then we're going to look at to see where on what interval do we have the signs matching up, right? So if the signs match up between velocity and acceleration, we know that speed is increasing, and then we can identify that range for our answer. Okay. So it's basically like first derivative test and test for concavity, but this is in context of particle motion. All right. So first thing, let's go ahead and find velocity. Then we'll set velocity equal to 0. Then we'll find critical points. So basically the same steps as we did with first derivative test, which is now we call it particle motion. Okay, so let's find velocity first. Go through power rule. Okay, this is our last problem. Okay, we'll be done after this. Okay, so B of t equals
P cubed becomes P squared minus 24t. Set equal to 0, we can factor out a what? 3. Okay. PCF of 3. Multiplies to be 7, adds it to be -8. P equals 1 and 7. The only criteria that we have for our sign line is that it's going to be positive. So we're going to start at 0 and move forward. So velocity sign line. I'm going to put my velocity sign line here so I can just eventually kind of line everything up with the acceleration. So I want 0 to be my starting point. 1, 7. All right, I'm going to test each interval here. So I'll choose 1/2. I'll choose 2, and I'll choose 8. I like to test against the factored form. Feels a little bit easier. 1/2 then for t. 1/2 minus 7 is negative. 1/2 minus 1 is negative. Negative and negatives gives me positive. So I know for this interval, my object is moving to the right. Okay, plug 2 in. 2 minus 7 is negative. 2 minus 1 is positive. So that's negative 8. 8 minus 7, 8 minus 1, both positive. Right. We want to know where the speed of the particle is increasing. We have to compare this with our acceleration sign line. So let's make our way down to acceleration. Go through power rule again. A of t equals 6t minus 24. Again, set equal to 0. GCF. The only critical point that we have here is 4. Okay. So I'm going to put acceleration right below my velocity, but I'm going to try to line it up so I can kind of match my parts here. All right, so find critical points. So I'm going to test 1 and 5 into my acceleration. So 1 minus 4 is negative. So I know in this interval, acceleration is negative. To the right of 5, though, positive. So I'm looking for an interval where the speed of the particle is increasing. So therefore, we want both velocity and acceleration to share the same signs. So can you identify the intervals where both velocity and acceleration have the same signs? Between 1 to 4, okay. They're both the same signs there. Or else? 7 to infinity, yeah. Between 1 and 4. And then greater than 7, yeah. Okay, any questions?
Yeah, just one thing here. I just want to make sure that we understand that I know we went a little off track with the calendar because I switched the days for the first assessment, but now we're back on track. So we should be able to follow the homework assignments and the due dates with the calendar that you have. So I checked 9 through 12, and then after break, no homework due on Monday, but on Tuesday, I'll check pages 13 through 16
as well as pages 1 and 2 from when we get back after the break with our, but nothing to, but I do want to encourage you that if you have time that you would like to chip away at that assessment 4, that FRQ packet, you can kind of make your way through that, but no homework over break, but just wanted to give you a heads up as to what's coming up. Yeah. Oh, yeah, I haven't given this out to you, so I'll give it to you when we get back from break. Okay, come get your phones.
I didn't want to do anything.
No, I have to go.
And then she showed me how her phone. You sense it, sense it to me. That is. You nasty.
Do you have some packets that's for after spring break already?
Yeah.
I was just wondering, 'cause I was gonna go. I was gonna go today, so let's just go ahead.
You do have the FRQ.
So wait, I started to get that.
What an upstanding student.
Ready?
Literally.
Yeah, upstanding. Thank you. And then.
So this is the IP3.
Yeah.
And
Awesome. And then just. Go first and second.
And I'll get you the poster.
Okay.
Thank you so much.
Oh, heck no. Y'all are friends, right?